are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about application of nanotechnology in hydrogen storage and polymer. So, different type of hydrogen storage materials is available. So, in solid phase hydrogen storage particularly, so that we will discuss. So, before we will discuss about the different type of nanomaterials that can be applied for a hydrogen storage. So, before that different mode of hydrogen storage, so that we will discuss, means hydrogens, what are the way we can store and where it can be applicable, so the nanomaterials to improve the storage efficiency of hydrogens in that particular materials. Okay. So, different type of examples we will give, means we already have studied that different type of metals, metal oxides and carbon based nanomaterials that can be prepared by considering different methods. So, that already have discussed. So, now if we look into the hydrogen storage, so hydrogens, that is actually we can store in gas phase, liquid phase and solid phase. So, in solid phase storage is the most safest way of storage of hydrogen. So, there that hydrogens we can store physical based hydrogen storage materials or physical options based hydrogen storage that we can do, or chemical options based hydrogen storage we can do. So, both the things we will discuss. So, and for that different type of materials also can be used, means considering the dimensions of the materials, that may be 0 dimensional materials, 1 dimensional nanomaterials or 3 dimensional materials or bulk materials. So, that we will consider, and these are the materials MOF or COF type of materials. So, or bulk mesoporous materials. So, that would be used for a specific metal hydride or complex hydride. So, where these particular nanomaterials can be used if certain percentage to improve the storage efficiency of hydrogen in that particular material. So, in chemical options, these are the physical options, and chemical options based metal hydrates, that is magnesium hydrate, sodium aluminum hydrates, these are the metal hydrides or complex hydrides, that would metal hydrides or complex hydrides that would be discussed. Okay. So, in the beginning, if we say that hydrogens, there are different modes of storage: gas phase storage, compressed gas storage, cryogenic or liquid phase also storage, and solid phase storage. So, in this particular nanomaterials, that also can be stored in cryogenic, cryocompressed, where liquid phase of hydrogen that can be stored as a catalyst, nanomaterials as a catalyst, that is maybe nano iron oxides or other materials that also used in the storage tanks, that we are not going to discuss. Only solid phase storage of hydrogens, whence hydrogens can be stored in the form of complex hydride, metal hydride. So, there we can use different type of nanomaterials, and here two different modes of storage, that is the physical options and chemical options. So, that we will basically discuss. So, here different storage tank, that is the compressed, cryocompressed and liquid hydrogen. So, that we are not going to discuss, but these are the mode of hydrogen that can be stored. So, here hydrogen storage systems in Japan are different storage systems, alloy based storage systems, metal hydrides based storage systems are available. So, that is 120 kg of hydrogen that is being stored in lanthanum nickels type of alloy, metal alloy. So, that was used to store hydrogens. So, here productions of hydrogens, that is also important, means hydrogens are different way you can produce. So, in solar water electricity, that way we can produce, and that can be store and transport, and then finally supply for the electricity that can be used. So, here wind power, solar power, their hydrogen can be stored. Okay. So, in metal hydride tanks, so here hydrogen actually can be stored, so in the form of metal hydrides or absorbing materials, and after that, that can be used when it would be required for a specific application. So, here hydrogen storage different materials, so that can be used to store hydrogen. So, here I said for particularly a solid phase hydrogen storage, that approach we will discuss, physical options based and chemical options based here. And physical options based, actually here nanoporous adsorbents materials that we can use for physically, that hydrogen molecules will get adsorbed over the surface or pores that is present in that material. So, and in chemical options, so there's different type of adsorbents materials is available, so metal adsorbents, where hydrogen can be stored by formation of strong bonds. So, in two different cases, one or two examples we will discuss. Okay. In physical options based, here you can see that materials, if having pores, different type of pores, or the materials we will discuss having exceptionally good surface area or high surface area. So, and various type of micropore, mesopores present, and there when molecules hydrogen molecules come in contact and they remains in that particular pores, so they will be adjusted through van der Waals force of interactions over the materials having the pores. Okay, so different type of material, that is MOF, COP is available. So activated carbons, zeolites, fullerenes, these are the materials available that can be used for this particular purpose. So here using options based hydrogen storage materials, I said different type of metal organic frameworks, activated carbons, zeolites or carbon nanotube fullerenes, organic nanoporous polymers also is available that can be used. So in this type of materials actually there is some advantage, means here the absorptions and desorptions kinetics is very fast and reversibility is also very good in this particular fused options way of hydrogen storage. So means sometimes this type of storage required very low temperature, maybe 77 Kelvin liquid nitrogen. So temperatures or room temperature also we can do, but once we go for very low temperatures, so then the storage capacity exceptionally increase as compared to the room temperature. So that is the limitations of this type of storage in fused options way of storage of hydrogens. Okay. So here chemi-absorption based storage also means a strong chemical bonds is present with the hydrogen atoms and the storage materials or the storage surface. So that bonds may be ionic bonds or maybe covalent bond that is formed via electronic sharing or transferring of electrons. So here in this type of materials having high surface area, also the advantage is there, this types of the materials having high storage hydrogen density. Limitations is the slow kinetics of these type of materials and irreversible or partially reversible at practical temperatures when these materials would be used for storage of hydrogen. Classifications of the chemi-absorption materials, that we can see metal hydrates, that is direct combinations of the metals with hydrogen. So magnesium hydrate types one of examples, or some light metal based hydrogens or metal hydrates, that is complex hydrates, you can say lithium aluminum hydrate, sodium aluminum hydrate, this type of materials. So that materials also consist a high weight percentage of hydrogens. And some complex, these are also you can say complex metal hydrates, means lithium aluminum hydrates or sodium aluminum hydrates. So here these are the materials having, materials can be used as a storage materials, but sometimes when we absorb hydrogen in this type of materials, so that can stores hydrogens, but when we need to release means hydrogens from those materials, then we have to use high temperature. So that is the disadvantage of this type of materials, means sometimes when we are going to store any hydrogens from in any materials, so then reversibly that materials can dissolve that hydrogens, what are the hydrogens that being stored. So sometimes we need to use high temperature, so that is the disadvantage. Therefore to down the temperatures, means desorption temperature, sometimes we have to use different type of catalyst or nanomaterials, metal oxides or carbon based materials that actually down the desorption kinetics or desorption kinetic temperatures also that can be down. So therefore that can improve the means storage means performance as per DOE expectations or DOE means criteria, so that can be fulfilled. So here's a different type of class of materials we have discussed. So 0 dimensional, so 1 dimensional, 3 dimensional, 2 dimensional, different type of materials. So that already we have discussed. So 0 dimensionals, 1 dimensional, 2 dimensional, 3 type of nanomaterials that is available. So these are the things we have discussed. So now apart from that, so organic nanomaterial, inorganic nanomaterial, hybrid nanomaterials or carbon based nanomaterials, so that also can be used for storage of hydrogens, means hydrogen storage applications, particularly direct fused options or as a catalyst also we can store. Okay. So actually when, so this type of materials when we are using in the fused options process, so here first we will discuss about zero dimensionals based hydrogen storage materials. So here actually here you can see, so if we talk about nanoporous silica nanomaterials, that is made from rice husk, so and then particle size that may be 50 nanometer approximates, and this type of materials having 226 meters square per grams, that surface area, and this type of materials can uptake hydrogens 0.348% of hydrogens at low temperature, that is 77 Kelvin and 19 bar pressures that we have to use. So Here temperature is exceptionally low, 77 kelvins and 19 bars. So that amount of hydrogens we can store these type of silica nanoparticles, or also polypyrrole nanoparticles that also can absorb hydrogens 2.75 weight% at 77 Kelvin and 80 bars. So these are the actually the hydrogen that these type of nanomaterials being stored by direct physics. Okay. So here's this type of materials are nickel nanoparticles on porous carbons. So that materials also can uptakes hydrogens up to 4.29 weight% at 77 Kelvin and 5 bar pressures. And at room temperature usually this material stores very less amount, so that is 1.69 weight% at room temperature. So here's these materials means when we are maintaining 77 kelvins extremely low temperatures and 5 bars, so then it can store up to 4.29 weight% of hydrogen. And when we are using room temperature to store hydrogen, so they are 1.69 weight%. So nickel nanoparticles, that is porous carbon based materials. Even some other metals also can be used, our activated carbons, that also are good materials for storage of hydrogen. So here zero dimensional based hydrogen storage materials, that moss of bamboo that was used as the starting material, and then carbonizations or activations, nitrogen doping, platinum doping. So finally that bamboo AC carbon activated carbons, over there nitrogen activated carbons. So platinum was dispersed over there, platinum nanoparticles. So that can store a good amount of hydrogen. So here's directly activated carbons or nitrogen doped and then platinum doped at different percentage was showing. So if we means use platinums nanoparticles that is distributed over the activated carbons, that is being stores good amount of hydrogen. So here you can see the hydrogen uptakes at 77 kelvins 1 bar. So activated carbons only stores 2.78%. When it is doped with nitrogens, it can store slightly improving in the hydrogen storage capacity. And whence it would be doped with some other metals that not significantly improved, but it also can stores the hydrogens, but that is room temperatures. Okay. So here hydrogen uptakes at 298 kelvins and 40 bars, that pressures was used. So here activated carbons you can see at 77 Kelvin, it is being stored 2.78% of hydrogen, and when the temperature is high 25 degree centigrade or room temperatures and high pressure, so then only 0.48% of hydrogen that can be stored. So, okay, not good amount. So if these are the materials, if you want to use as hydrogen storage materials, so then you have to go for very low temperatures close to 77 Kelvin. So then we can get good amount of storage of hydrogen. So here you can see that list of the different materials. Here's nitrogen doped activated carbons that is used for storage of hydrogens, Fiji options. So at 77 kelvins 1 bars, that amount of it can be stored, and platinum based materials at room temperatures, it being stored means depending upon that adjacent temperatures, that amount of the hydrogen that stored different amounts. Okay. So then one dimensional nanomaterials for hydrogen storage. So here carbon nanotube based or single wall or carbon multiple carbon nanotubes. So that is here you can see. So hydrogen uptakes not good amounts at room temperature and 100 bar, approximate 1% of hydrogen that can store. Normal conventional carbon nanotubes, when it is functionalized with the different hydroxyl groups, so then or acidic groups, it can improve slightly. Here you can see means it was done at room temperature 100 bar. So here's pressure slightly lowered, so that was 80 bar. So then hydrogen uptakes at room temperature, so 0.65 weight% and 0.89 also. So different here you can see. So here's crystalline type of carbon nanotubes and functional nanotubes at 100 bar. So here the comparisons you can see. So the hydrogen uptakes of P type of CNT and functionalized CNT that would store much more amount of the hydrogens as compared to the non-functionalized CNT. Okay, so here you can see means there are different type of pores present. So in that particular type of CNT, when it is functionalized, so that functionalized groups can help to store more amount of hydrogens. Okay. So here nickel dope activated carbon nanofiber also. So here you can see extremely high pressure is required. So hence nickel doped activated carbons was used. So here not normal carbon nanotubes, hence it was used at 298 kelvins and 40 bars. So it is being stored 0.26 weight% of hydrogens, and hence that pressures has been increased to 4200 bar. So there you can see that and nickel was doped. So then the activated carbon nanofibers that is being stores more amount of hydrogens. So here different type of one dimensional materials, so that has been discussed. So depending upon the materials, so the hydrogen storage capacity also increase. So here also different two dimensional materials, that is the graphenes or reduced graphenes or metal decorated graphene oxide. So here I am not going to discuss more details. So here it is given. So here you can see when we are using a normal graphene oxide, so it can uptakes up to 1.9 weight% of hydrogens at room temperature and 80 bar pressure. So in this case extremely high pressures we have to use, so 80 bar pressure. When that same materials is reduced, so that is reduced graphene oxide, that is being stores comparatively lower amount of hydrogen. So 1.3 weight% of hydrogen that can uptake at room temperature and 80 bar same pressures. So graphene oxide is storing much more better amount of hydrogens, good amount of hydrogen as compared to the reduced graphene oxides. If we dope different metals, that may be alumina or lithium, that simulated works actually DFT calculation, Monte Carlo simulations that was done, and here it has been showing that it may stores a much more higher amount of hydrogens at high pressures, extremely high pressures we have to use, so 100 bar pressures. Okay, so here different type of actually graphene oxide was taken. This is graphene oxides and this is graphene oxides. With graphene oxide titanium was impregnated, so graphene oxide titanium composite was made, and here that same materials was reduced and three different materials was compared. So and three different amount of means when that materials was titanium and graphene oxides. So here hydrogen uptakes is was good amount and reversibility was found 80% reversibility in this the amount of hydrogen that is being stored. So when it is being reduced, so reversibility is slightly lower. So means either we can use means titanium graphene oxide. So in that case the materials would store good amount of hydrogens, at the same time so there is the reversibility of hydrogen what are the being stored. So that would gives much more better reversibility as compared to the reduced graphene oxides, where titanium and graphene oxides was used to make that composites. Okay, so here also others means palladium decorated graphites or graphenes that was used. So here also palladium decorated graphenes you can see that can store some much more higher amount of hydrogens as compared to the reduced graphene oxides. So here two dimensional different materials, graphene oxides, reduced graphene oxides. So at different temperature and pressures you can see it can stores different amount of the hydrogens. Okay, so and when different type of platinum, palladiums or materials was impregnated, so the storage amount of hydrogen slightly increased, but at the same time so the absorption pressure also has increased. So depending upon the materials and absorption pressures, so the quantity of hydrogen uptakes will increase or decrease. So depending upon that at what temperature we are observing. So if it is room temperature, then absorption amount is very low. It is very low temperatures close to 77 kelvins or liquid hydrogen temperatures, liquid nitrogen temperature if you are able to use. So then good amount of hydrogens, higher amount of hydrogens that can store. And even at low pressures, the hydrogen storage or adsorption amount is very low. Once we are using extremely high pressure 80 bar, 100 bar pressures, then hydrogen storage capability increase. So apart from that, there are three dimensionals or 3D type of materials. So nanoporous materials, basically MOF or COP type of materials. These are the materials having different type of pores that already have discussed, and these are the materials composed of different type of organic or inorganic or maybe hybrids materials. These are the materials, so that can be used as a hydrogen storage materials. Here's detailed synthesis I am not going to discuss, but different type of MOF type of materials. So how much quantity of hydrogen these are the materials can store, so that basically you want to discuss. So here you can see MOF 5, and that was zinc MOF, that was store approximately 4.58% of hydrogens at 78 kelvins and 20 bar pressures we have to use. And once we are using MOF 210, so here hydrogen uptake is more, but here pressure is extremely high, 80 bars we have to use, and temperature is almost close to 78 kelvins. So if we go for high pressures or low temperature, then extremely good quantity of hydrogens it can be stored in this type of materials also. Okay. So here different type of structures and how they can store, so that has been discussed. So I am not going to discuss more details. So here's covalent organic frameworks that also can be used for hydrogen storage materials. So here COF5s that can store hydrogens 3.8% at 77 kelvins and 80 bar pressures. So 3.58%. So good amount of hydrogen it can be stored, although we have to use at very low temperatures. So similarly, some COF 102, that is engineer COF 102 derivatives, so that can stores that much amount of hydrogens at 100 bars. So and at 300 kelvins 6.58% that can be stored. So in this type of materials actually the surface area means maybe increased, so due to that pore volumes and other things that has been changed, so therefore these type of materials have been modified, as a result good amount of hydrogens that can be stored. Okay. So here activated carbons or other materials also can be used for storage of hydrogens. So here from different source these materials can be used to prepare these activated carbons, and that can be used for the storage of hydrogen purpose. Okay, so here you can see different type of have been tabulated form. So here MOF5 that materials can be used for adsorptions or hydrogen. So here's this temperature and 20 bar, so it is stores 4.58%, and COP5 you can see that is also at the temperatures, so close to, but here pressures is extremely high, adsorption pressures. So here MOF5 it was used 20 bar, so as compared to the MOF, so COP5 materials, so we need high pressures to store 3.58% of hydrogens. So different type of materials are there, so that is we can prepare, means metals, metal oxides or activated carbons, MOF type of materials, COP type of materials. So there we can impregnate different type of metals, and by maintaining low temperatures, high pressures, we can store good amount of hydrogens. Okay, that is physical storage based systems or materials or process. Now chemi-Johnson's process, in this type of process actually we can classify the materials into different way. One is metal hydrates, another one is the complex hydrates. Okay. So in metal hydrates these are the examples. So lanthanum, nickels, these are the examples of metal hydrates. And complex hydrates, different type of sodium aluminum hydrates, lithium aluminum hydrates, these are the materials we can say as a complex hydrate. These are the materials can be used to store hydrogens reversibly. So here when these are the materials we store hydrogens, and reversibly we want to dissolve those materials, so hydrogens from those materials, so then we have to use some catalysts. Okay, so here's different type of nanomaterials you can see. So here for examples MgH2 also, that also can be used as a hydrogen storage materials. So here with these materials means if we want to get hydrogen from this material, so required extremely high temperatures we have to use. So if we want to down these temperatures and to get the same quantity of hydrogens, then we have to use catalyst or nanomaterials, different type of nanomaterials we have to use. So then we can down the temperature, dissolution temperature or cyclic means study. So where hydrogen can, once it is get adsorbed, and then if you want to dissolve the hydrogen, adsorb hydrogen, so then first we have to take nanomaterials, and then we can impregnate catalyst over there. So catalyst and nanomaterial composite we can mix, and that directly we can, this composite we can use with that metal hydrates. So and if we maintain some temperatures, so then we can get hydrogens, means from these hydrates we can get hydrogens. Okay. Or else what we can do, so different type of nanomaterials we have, so metal oxides. So with the hydrates, these same materials, so we can mix them out. Then a particular method means solvothermal method, or means different type of means milling process is there, cryogenic milling or ball millings, or means facile solution methods. Many methods are there. So where nanomaterials and hydrates both would be mixed up. So then this type of composite means nanomaterials will be distributed in the crystals of hydrates, and then if we heat it up, so then we can generate hydrogens. So just physical mixings, or maybe with that hydrates we can mix, and then we can get that hydrogens reversibly from those materials. So here's a different type of titanium niobium doped materials, or chromium oxide, directly niobium oxide can be, or vanadium doped, nickel doped materials, nanomaterials can be used with the magnesium hydride MgH2, that is the hydrogen storage materials. With that means here's magnesium hydride was taken as the hydrogen storage material, that is the metal hydride. So with that means niobium oxides, titanium or nickel based nanomaterials, any materials we can impregnate or we can mix up with these metal hydrides, and then we can use those materials, composite materials, as hydrogen storage materials. So the roles of those nanomaterials is to down the temperature, desorption temperatures. As a result, the desorption kinetics would be higher or better. So here you can see the hydrogen storage capacity of MgH2, that is 7.76 weight percent hydrogen storage capacity. So these materials, when it is niobium oxide is doped, so it can store reversibly, I think approximate 7.08 percent of hydrogen. So here's even graphene composite also, or graphene oxides also, we can activated carbons also we can use as a catalyst or nanomaterials that with the magnesium hydrides. So that can also reversibly can stores hydrogens good amount of. Here activate graphene oxides was used, it can store 5.6 5.48% of hydrogens, and when activated carbons was used 6.63, and graphene oxides was used, or graphene composites. So that particle size is, here it was 6 nanometers, here it is 3 nanometer. So in particle size is changes means 6 nanometer to 3 nanometers. So slightly the storage capacity is slightly increased 5.4 to 5.6 weight percent. So depending upon the nanomaterial size and type of nanomaterial, the storage capacity also would change. Okay. So here I am not going to discuss more details about, actually here magnesium hydrides, that was the materials, metal hydrides. So apart from that, lanthanum nickel 5, that also can store hydrogens 1.37 weight percent, and some other materials is also there, so that also can store a good amount of hydrogens. And here these two means MgH2 with that these nanomaterials, and MgH2 zirconium nickel palladium nanopowders that can be impregnated, means these are the nanomaterials that can be used. This is the nanomaterials that maybe acts as a additives, or maybe acts as a catalyst that improve the hydrogen's storage capacity, means in terms of desorptions, means these are the materials we use for storage of hydrogens, particularly absorptions and desorptions process, that materials would absorb hydrogens, and when it is required it would dissolve the hydrogens reversibly. So by that way we can use means the hydrogens for different applications purpose. But the storage I said, so different nanomaterials I said, so iron based nanomaterials that can be doped with the MgH2, so that can improve the storage capacity, and desorptions temperatures also that can be down. So that is the objective, actually these are the different type of metal oxides, carbon based materials why we are going to use. So actually to down the activation energy or desorption temperatures, so then at low temperature we can get good amount of hydrogens once we use different type of catalyst or nanomaterial catalysts. So here you can see as per DOE targets, so the material should have activation energy 30 kJ per moles of hydrogens, and it may stores 3 7.6 weight percent of hydrogen. So gravimetric storage capacity, and as per DOE target is this, so less than 85 degree centigrade, so within less than 100 degree or within 85 degree centigrade less than equal to 85 degree centigrade, it can store 7.68% hydrogens and it can give within 3 to 5 minutes. So that is the DOE targets, and as a result the activation energy of those materials would be very low. So in real case actually whatever the materials we are going to prepare, so that having little bit higher activation energy and the material is following like this. So in case it is required instead of 85, it requires high temperatures. So it is not desirable. So activation energy is high, therefore active degestion temperature is very high. So these are the means a particular catalyst you have to choose which can down the activation energy of these materials, and also digestion temperature also we have to down, and within very short period of time, so that materials would give good amount of hydrogens. So here different type of materials, metals based or that can be used for magnesium hydrates with that material. So here see comparisons you can see, so different type of metal oxides, that niobium, irons, vanadium, manganese, silica, copper, alumina, different type of metal oxides that can be used as a catalyst materials with the MgH2 as a hydrogen storage materials or metal hydrates, complex hydrates you can say. So these hydrates, with that any of these metal oxides means nanomaterials we can impregnate or we can make a composite materials, so that can easily store good amount of hydrogens and release good amount of hydrogen. So here these materials can absorb say approximate 7-8% of hydrogens in 60 seconds, and for digestions it would takes 130 seconds approximately. So this naive is much more effective as compared to the other metal oxides and nanomaterials for this particular storage of hydrogens in magnesium hydrates. So here's JDAR's nickel palladium nanopowders that can be also used as a catalyst or maybe additives for this particular magnesium hydride. So here also you can see if we do not use any additives or catalyst, this catalyst no catalyst, so then the hydrogen absorption capacity is very low, it is close to 2-8%, and whence we use means 40 these materials, and after 40 hours you can see it can store good amount of hydrogens close to 5.5-5.8% within 2 minutes. Here's after 40 hours of milling. So you can see after 40 hours of millings it can store close to 5 or 5.5 approximate that 8% of hydrogens, but within 2 minutes, so it can store close to 5, and if we wait for 10 minutes, so close to 6 or 8% of hydrogens it can store good amount of it. Similarly, once we are going to do the study of degestions, this is absorption study and this is degestion study. So same materials, when we are going to take out hydrogen from those materials, so then within 40 hours whatever that means MgH2 and zirconia, nickel, palladiums, these nanopowders or nanomaterials was composite, it was milled for 40 hours. So then that materials dissolves hydrogens, you can see within very short period of time good amount of hydrogen, so that is close to 5.5 or 8% of hydrogen that can dissolve easily. So here you can see, so 5.78% of hydrogens within 4.6 minutes at 175 degrees centigrade it can dissolve that amount of. So that is the role of these type of nanomaterials or nanopowders we can mix up with MgH2 that can gives good amount of hydrogen. See here cyclic study was done, so means to check that materials whether how much good is that materials. Okay, so that materials can gives a good amount of hydrogens that can store reversibly. Okay, so next is sodium aluminum hydrates, that is another complex hydrate, so that can be used as a hydrogen storage material. So with that the 9-8% of TiO2 carbons, nanocrystalline Ti2 and carbons that can be used as a catalyst or additives with this type of metal hydrides or complex hydrides, that also can store hydrogens good amounts with reversibly. So here you can see the disruptions amount of hydrogens. So, when only sodium aluminum hydrides was used at 140 degrees centigrade, it can dissolve very low amounts of hydrogens. Okay, so up to 180 minutes. So, you can see the amount of hydrogen storage or disruptions, that is very low amounts. So, whence we are using titania carbons nanocrystalline materials with this. So, means we have to use sodium aluminum hydrides NaAlH4 with that TiO2 carbon composites. This is the nanomaterials that if we a certain weight percentage if we use and make a composite material, so that dissolves a good amount of hydrogens, that is close to 4.28%. So, here 4.28% of amount of hydrogens we can gets within 10 minutes. Okay, so then this type of materials means this is the rules, means the disruptions amounts you can see from this to this. So, it has been increased. Even the materials also can store reversibly, means absorptions and disruption study was done. So, it can up to so many cycles. So, it has been observed that it can reversibly stores good amount of hydrogen up to 4.46 weight percents of hydrogens that was studied. Okay. Some others metal hydrides, also AV pipes or lanthanum nickel pipes, that materials also can stores 1.48% of hydrogens, that is good amount of hydrogens that can be stored, but here the pressures is very low pressures, means close to 4 bar pressure, and temperature is 50 degrees centigrade. So, extremely low temperature. So, not low temperature, good temperature. So, here's amount of storage percentage is 1.48%. So, that is also significantly good amount as compared to this temperature and pressures. So, these materials also means metal hydrides can be used as a hydrogen storage materials. So, these materials also can store hydrogens reversibly, and with that materials means some others catalyst also we can use, or we can use different nanomaterials to improve the performance of this type of materials. That also means so far it is giving 1.48% of hydrogens at this particular temperature. So, using or different type of nanomaterials also we can improve this performance, storage performance capacity of this type of materials. So, apart from that, there are other some metal hydrides also available. So, alloy type of materials that also can stores good amount of hydrogens, but not significantly good amount, but it also good things is at low temperatures, means 50 degrees centigrade. So, and low pressures. So, it can disruptions temperatures, actually this is disruptions temperature and pressures. So, 50 degrees centigrade is the disruption temperature. So, this is good amount. So, actually here if we talk about sodium aluminum hydrides, here we have to go for 140 degrees centigrade. So, comparatively lanthanum nickels metal hydrides. So, here high temperature you have to use, and in that case lanthanum's nickel 5. So, here we have to use 50 degrees centigrade. So, therefore, this is compared to that it is much more better, but hydrogen storage quantities 1.48%, very less quantity or low quantity as compared to this. So, means somehow we have to compromise with the temperatures and weight percents of hydrogens, means disruption temperatures. Okay, so thank you. So, today is up to this. Okay, so we have studied different type of nanomaterials and different type of metal hydrides. So, complex hydrides, so where different type of carbon based metal oxide based materials, nanomaterials can be used to down the disruption temperatures of those metal hydrides or complex hydrides. As a result, we can down the disruption temperatures, we can improve the storage performance or storage capacity, weight percent or volume percents of hydrogens in those materials by using different type of nanomaterials. That is the role of nanomaterials, that can acts as a catalyst or improve the storage performance of these materials. So, thank you. So, today is up to this.